So let's get going. So welcome back to the second half of this class, this first class. If you look at the class syllabus, which your TA is going to distribute, there are actually quite a number of very decent reference that I've given you here. Lots of time it's worth to have one or two, I guess, reference book by your side. Some of these I actually have in PDF form. So if you get in touch with me, I can send you like a PDF excerpt or something, although it's not for general distribution. Some of this book I just searched. Some of these I just went to some library and picked up randomly, and I found out it's good, very good description of what the subject is. And a lot of these articles are also online, and you can learn a lot of stuff from like toward data science blog or so forth. Okay, so there's plenty of stuff. So no need to worry about it. Okay. First of all, I want to start the second half by talking about this Wolfram Mathematica platform. It's well, it's a bit expensive, so I hope you make a good use of it. You can only have license for it during the duration of this class, but if you're a student, you can get it very cheaply. Okay, using your .Chulalongkorn ID, I think, email. Anyway, what is Wolfram Mathematica? Well, first of all, this is not a programming language in the traditional sense that you think of. It's actually a bit of a software as well. It's sort of like a computational platform. It was actually created by physicists to solve physics. Basically, it wasn't meant to be like a general tools like general language like C or Python or R or something like that. Okay. Now, what makes it? I'll give you a sort of like a con of using Mathematica, which is that it's a little bit like iOS. So it's kind of like a closed system. Okay, it's not an open system. It's not like Android. So you don't have as big a user community as say Python, which is an open thing. But number one, it's more powerful. It in certain way and less powerful in a certain way. It's more powerful in the fact that it's actually an analytical engine. What I mean by that is that it actually understands mathematical symbols. It knows what infinity is. It can sum to infinity. It can perform. It's just not a general language modeling. For example, let me just show you this. Okay, and this is just may not mean anything to you, but let's go to for example, okay, just for fun. This is completely random. Well, not random, but I chose this, right? This is actually a summation, a double summation over I and j, right? The outer summation goes from I going from 1 to infinity. The inner summation going from j to I. So it's sort of like a nested summation, okay? You cannot do this with Python, R, C++, or anything, okay? I think maybe there's something like Julia might be able to do it. I'm not quite sure. But basically something like this. Turns out, okay, is equal to pi to the power 4 divided by 1, 2, 3. This is not numerical. This is not approximation. This is actually a real answer. It does mathematical convergence for you, something like that. Likewise, you can do this. So Now, this thing here is an integral from, say, 2 to infinity, e to the power minus 3, okay? This, if you were to represent this in, say, with R or Python, you have to transform it into a function call to a numerical evaluation, okay? But this is actually a real property. It's 1 over e to the 6. Anybody know what this is, by the way? This is exponential distribution. This is a bit like when do you expect to die? Okay, obviously not 3, but you know, yeah. So something like this is expected lifetime of a machine lasting from 2 years to infinity. Well, it's actually, if I want a number to it, 0.02 years or something. I don't know. Okay, so if this were a model of a machine, okay, provided it lives beyond 2 years, it's going to live another 0.02 years, something like that. Doesn't matter. Okay, but the point is, this is very powerful. This is symbolic. This is powerful. Again, the downside is that it's a closed system. Now, this is not something that's relevant to you or this class. What's relevant to you in this class is that the guy who created this and the team is kind of like well, they're very good with programming now, obviously with computing, but they were like physicists, I guess. And physicists don't want to do tedious job. You know, my undergraduate was in physics, so that's, you know, I'm very lazy when it comes to tedious job. So what happened is that some of the routine analytics, okay, that's done in Python and R is done so often that, you know, guys like me, you know, or physicists, they say, well, if we do this all the time, why don't we just sort of like encapsulate it in a higher level kind of thing? So it's not just a functional programming language, it's more like a high level. So instead of saying, okay, this is how you build a neural network, because the way you build neural network takes up, say, 100 lines, and you do this all the time, again and again and again and again. So when you have a new application, you just copy paste and whatever. They get bored of this, so they just try to encapsulate all this into a higher level. So what ends up happening is that you would use function like, you know, build me a neural network. End of story. Now, what it means is that some of the specificities are treated as default argument. Okay, so it's like saying, instead of having a language that tells you how to build a building and you have to say how tall the building, how long, how window size, how many stairs, all these specificities, right? You sort of like notice, wait a minute, you build a lot of a 2-story house and they tend to look a little bit like that. Why don't we have like a default parameters? Okay, so you can call a function called build a house, and that will build you a function. Build your house, and that house will have 2-story, standard size window. Everything is all default. Okay, now if you don't want that, you can specify, but at the same time, at the top level, you don't have to, you know, you don't have to be very fastidious about individual parameters. So it's very high level, and that's why it's very good for bite-sized student. Why? Because many of you, even though you're in this class, are probably gonna like major in things like, say, smart cities and inclusive community, health and well-being, sustainable development. Some of those areas you might want to use analytical tools, but you're not, you know, going to be the real data scientist about it. You're not going to perform the experiment. So you want something like quick and dirty. So you might have some, I don't know, some data set that has to do with health system, and just say predict requirement, how many beds, how many doctor per 100,000 do you need in a typical tambon or something like that. And that can be done with a machine learning. Okay, so build me a machine. So nowadays, you guys are even going to another step. You say, well, in the future, you don't even have to do this in Mathematica. You use ChatGPT or something like that. Well, the thing is, ChatGPT is done by what's called associative memory. Deep down, that's what it is. So in that, it cannot build you a quantitative model per se. However, there's some work to it doing that. So instead of saying, you know, build me a neural network that predicts how many doctors do you require for 100,000 people in a village or something like that, ChatGPT would have like a back end, And that back end would link to what's called Wolfram Alpha, which is kind of like get you back to Wolfram Mathematica in a roundabout way. Okay. So until that day happen, it just is easy for you to have a high level specification of what you want to do. Okay. So it's a bit like it's like, you know, I have X, I have Y, build me a regression analysis. Okay. Now, if you are smart and if you want to be a professional, you would try different things and you would try different specific thing, different algorithm and so forth. And you can specify that. Okay. But top level, you can do that. And let me show you. So that's what I have to say. I can show you a little bit of example of that. So yeah, this could be something like this. So for example, let's say, and this is an example I just kind of made up. I have some data set, okay? This is a data set, and I just import it. Never mind, don't worry about it. And I intend to use this later as a sort of like showing the pipeline, but I thought I might as well show you how top level it is. But I'll tell you what, let me just do this. Okay, so this is how things let me just hide the code so you can actually see what's happening. This is an example of a complete data pipeline. Okay, first you have to import a label data. Okay, that means something like, in this case, iris data. I think you take a measurement of the flower and you try to identify the species. Okay, so this is like the hello world of machine learning. Okay, you see this all the time, but I want to show you the step. So you import the data, right? And then you import it as IO pair. What it means is that you can take the measurement to be X, and then you take the name of the flower to be Y. That's what you do, right? You split into training and testing. What this means is that you want to sort of like treat the data, instead of having the algorithm see the whole data set, have it see part of it, okay, training data, and then test on the data it hasn't seen. Remember, we want to generalize, right? So data is a sample of a bigger population. But when you develop the model, you want to anticipate how it's going to do with bigger population. The way you do it is take some of the data and hide it. Hide it. You don't show it to computer. Okay, you only show the computer part of the data, and that's called training data. And then the data that the computer doesn't know about, hasn't seen before, this becomes what's called testing data. And then you test the computer algorithm on this, see how it does. Okay, so this tells you how it performs. Now, this is what I want to say. This is how simple it is to say build a classifier. Okay, literally one function. Okay, this is my data set called training data. This is called classify. And once I train it, I build it. It's done. It's done. Now, this timing thing, I just put it just to show you how quick certain machine is. Okay, sometimes I like to test whether or not my laptop is faster or whatever. So basically, this is it. One thing. This builds the classification model. When I was your age, this would have taken me 200 lines at least, something like that. Now, it turns out this is done, and then it tests, and it does all kind of stuff, and it shows, you know, error, function, and all that. And this is all visualization to say, you know, out of this, how many times it gets right or it gets perfectly right. This is a training set. Oh, testing set, it gets 2 error out of, you know. So this is all one liner. So you get to play with this when you have your license. I was planning to go through a lot of this in detail, but apparently some of you haven't got it. So maybe I'll do it next week. Okay, that will take you through. So make sure. Okay. Sorry for some misunderstanding or whatever it is that some of you haven't got, but I think it's not just 1 or 2, but it's actually a third of the class. So make sure you got this installed. So next week I would actually take you through the Mathematica primitives, you know, how to define X or whatever, and how to build a model. But this is just to show you that it is powerful. it can build you, a data analytics as a one-liner. But of course, if you know what you're doing, you can actually do more, right? If you're an architect, you don't want to say build a house. You want to say build a house with this look, Victorian facade. I don't know. Okay, so you can be very fancy about it. So that's basically why I have, why I convince the school to purchase this license for students. It's very expensive. There are 100 licenses. Okay, so use it well. Now, how does it stand in relation to the programming world at large? Well, it's a bit like, again, like an iOS, it's a closed system. So if you have something that's new, like a new language model that comes out tomorrow, it's not going to be in Mathematica for a while, okay? It's going to be in Android or open system. And that's where Python comes in, okay? Python is completely general, so it can't do this thing. Another thing I'll show you is about visualization. But again, once you get the software, we'll work through them together and you'll see what I mean. But if you are in applied digital intelligence track, you will need to also be proficient, not just in Mathematica, but Python. The reason being that it's a general language, so a community of user is bigger. And also in terms of performance, a lot of numerical algorithm has a back-end processing in C or something, so it runs very fast. Okay, you know what I do in my professional life, and I think I looked up this kind of talk. I was giving a talk, I think. Maybe YouTube. Oops. Okay, maybe. What I do is this. I develop the mathematics and the program in Mathematica. So I work out all the relationship I want to explore, the user interface, the graphical interaction with the whatever client, whatever. Once I'm happy with it, I give it to my staff, who is very good at programming in Python. He then translates that into Python, because the real system, the solution that's implemented on the client's server will be on Python. I can't do that in Mathematica, first of all, because then there'll be a license issue, because but whereas Python is completely free. So if I work for a fund manager, for example, I also for the revenue department, they have a server. They install like a Python code base, and they can just run it. Okay, so I'm very clear about what I do. I do my algorithm development or my mathematics. Everything works out. I'm happy. I give it to my staff. My staff basically translate it, into Python, and that's what now. Some of you are so good. Some of you are so good in Python that you can start prototyping or working out the algorithm from beginning with Python without having to use the Mathematica in between. Okay, because you don't have to, all the nitty gritty programming parameters and codes, and you can explore in that. That's fine. Some of my staff do that actually. Okay. But again, this is a sort of like a very high level thing. It's sort of in computer language, it's called functional programming, but it has a flavor of what's called declarative programming. Declarative means you declare what you want done. Okay, it's not quite AI. It doesn't actually try to understand what you do. You still have to communicate to it, but you communicate to it at a top level. Okay, instead of just build a function that builds a neural network, say, I want a neural network with default parameter based on this data set. That's it. Okay, give me something. Okay, and then I refine it. So that's why it's very powerful. Now, today, so since we're not doing that this afternoon because we have to move that to next week. I'm going to do a sort of like a rundown on your background check a little bit. Okay, raise your hand if you've done linear algebra pretty much. Okay, no, hi, it's not a shame, it's not leprosy. Okay, so you're done. Good. Those of you who didn't raise your hand, you haven't done linear algebra. You haven't done linear algebra. Linear algebra, you don't even know what it is. You have or you have not done? Yes, raise your hand. Okay, then raise your hand. Okay, once let's start over. Who has learned linear algebra? Raise your hand as high as you can make it. Okay, that's good. That's everybody. Okay. How about calculus, differential and integral calculus? Okay, very good. Excellent. So now we're done. Okay. Why are those two important? Okay, and this is I'm spend some time on this. When I was your age, okay, we learned calculus in high school. We actually didn't learn linear algebra in high school. Kind of weird, huh? It's kind of weird. I didn't learn linear algebra in high school. Do you know why? Because if you think about it, during my age, my lifetime, when I was your age, data wasn't such a big thing. So things that require mathematics were of engineering in nature. Okay, so you need calculus because you have to do like mechanical system, and this is where differential equation and all stuff come in, right? Things like regression equation. Yeah, we did that, but in a way, you could get by without linear algebra. You can do a whole big summation, that sort of thing. Once data becomes a major part of your life, in other words, multiplying a whole bunch of numbers together becomes so ubiquitous. This is where they start to say, wait a minute, we start to need to teach linear algebra. We start to need to teach linear algebra in high school. Okay? So that's why linear algebra is everywhere. Okay? By the way, how many of you are like gamers or play like fairly fancy 3D games? No? Don't play games. Oh, you do play games, right? Do you know how those picture moves? Right? How do I move? Let's say I have a character that stands here on this part of the screen, right? In this 3D space. How do I move this point to that point? And I move everybody at once, right? So there's this guy, and because I'm changing perspective, I'm looking at the guy from over here. Okay? So all of a sudden, the coordinate of everything on the scene has to be changed all at once. All at once, right? How's that done? It's actually matrix multiplication, right? Your location in 3D space, okay? Your location in 3D space is a 3 number, right? So if I move you or I move my view of you, it has to move to another point in 3D space, right? How do you move from one point in 3D space to another point in 3D space? You multiply by a 3 by 3 matrix. Okay. Now, the game is 3D, but the screen you're looking at is 2D. How do I transform your existence in 3D as a computer character, a mouse or whatever, a rabbit, whatever, into location on a flat 2D? You multiply by 2 by 3 matrix, right? Okay. Now, of course, it's actually not a matrix. It's a tensor because you actually work in 3 colors. Okay. What's a matrix? Well, a matrix is a 2-dimensional array, right? So if I have a point in a computer screen, let's say I have 1,000 pixel tall, 1,600 pixel wide. It's a 1,000 by 1600 matrix, right? However, does your computer come in black and white or in color? Colors, right? So each point is actually a 3 number, red, blue, and green. So your computer screen is a tensor of dimension 1000 times 1600 times 3. And what's a video? Well, every snapshot is 1 dimension. So you have dimension in time as well, right? Okay. So all of this is matrix. All of this is matrix. So I'm trying to convince you with just, chatting alone. Again, you haven't got any computer in front of you that works in the way I want to show. So all this is matrix multiplication, right? All this is matrix multiplication. Well, let me draw you a little picture. Can I draw you a picture and paint or something? Is that paint? Is that paint application? Okay. Well, actually, you know what? I'm not very good with this, so I'm just gonna do hand waving. Well, tell you what, let's go to internet. Because I don't want to draw a picture from scratch. Neuron. Neuron. Okay. Let's look at this guy. Wikipedia, neuron. Okay. Okay. Right. Well, first of all, okay, I'm going to use my hand. You done linear regression, right? Y is equal to A1 x1 plus A2 x2 plus A3 x3, correct? Yeah. So instead of doing this, I write 1 is equal to, and then write A1, A2, A3 as a row vector. And I write x1, x2, x3 as a column vector. So it is a dot product, right? Right? It's a dot product. Okay, fine. So you know right away that in linear regression, if you're going to do a lot of this, linear algebra comes in. Okay? Simple as that. Well, let me show you another linear regression that lives inside your head. Inside your mind or head or your skull is about, I think, 200 billion neurons. Wait. No, that's number of galaxy. Hold on. A trillion, I think. A big number. Big number. Okay? Neuron. Each neuron looks like this. Each neuron looks like this. Okay? Each neuron looks like this. And look at the screen. หนูไม่สนใจเหรอลูกสนใจสกรีนไหน Yes, you. Okay. The neuron looks like this. Okay? The neuron like this. How does neuron work? Okay? Each of those little roots, it's a little bit like roots. It takes electrical signal. Okay? So you can think of electrical signal coming here. So these are all connected to the other neuron. Okay? Now, based on this, so you can think of this as x1, x2, x3, x4, x5, x6, x7, x7, 9, 10, 11, 12. Okay? Whatever. Okay? Now, there's also like a potential function. In other words, the signal can come in and sometimes it amplifies with certain coefficient. So you can think of A1, A2, A3, A4, A5, A6, A7, A8, A9, A10, A12. Right? The difference is with linear regression, you take the sum and you send the sum. The neuron is different. It has this thing called activation threshold. In other words, if you add up the weighted sum, so basically this is what? Let's say you have 12 here. So you have a dot product of x1 to x12 with a1 to a12. And if it's bigger than a certain number, it fires. It sends a signal. If it's not bigger than a certain number, it stays quiet. That's why it's called activation function. Okay, it's like you're hearing a whole lot of noise, but if it's not loud enough, you don't wake up. Okay, so that is the sort of like a threshold function. And now you again, when next week when you have everything, you will be able to plot it in front of your eyes. Okay, I can plot it now, but I think it's more fun for you to actually key in yourself. Okay, so today I'm just waving hand. So that is the non-linear stuff. That's it. Now, if you have a friend who is taking economics class or business here, they will do this thing called logistic regression. That's like their main tools in life, I think. Yeah, logistic regression is a little bit like that. You take A1 x1 plus A2 x2 plus blah, 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 and then you pass through this kind of non-linearity. If it's greater than a certain number, it's yes. If it's less than a certain number, it's no. So you can see why this logistic regression is very good for binary classification. Okay. So this here is a binary classification engine. Okay. This here is a binary classification engine. Now, I'm going to do another hand waving. Now imagine instead of having 12 input, I have just 2 input. One is the horizontal line in front of your class. The other one is a vertical going that way. So this is x1, this is x2. I can separate you into 2 groups based on any partition, right? Right? I have like a magic wand that say here, left and right, here, left and right. How do I create that line? Well, basically it's ax1 plus a2x2, right? And I say that, so I make ax1, a2x2, and if it's beyond certain point, I make it 1. Beyond certain point, I make it 2. So if I want to say that, let's say you're a bad student, you're a good student, and I want to make a transition here, right? I just find ax1 plus ax2 that draws this line, right? And if it's greater than that, instead of make it 1, I make it 0. Oh, I make it 1 for bad student, okay? This is a bad student detector. Okay? That's it. This is a binary classification. This is a logistic regression equation. This is a neuron. Now, think of how dumb that neuron is. That neuron can only separate you guys if you live across the street, a straight street, right? But if I want to single out, okay, just the 2 of you are bad, okay, how would I need to do that? How about 2 neurons? One goes this way, the other one goes this way, and chop the 2 of you off, right? So now I have just 2 bad students. So I can do that, right? In 2 dimensions, I can just need 2 neurons to think of that. In higher dimension, I can have as many neurons as I need. You have a trillion neurons in here, okay? Turns out that the Google GPT, ChatGPT, exactly the same thing. They also have nearly a trillion. I think they're not quite trillion neurons. But what they do is this. So, and here's the kicker. What does ChatGPT and Neuron and all this have in common? They do a lot of dot products. Okay? Your neuron does a dot product. Your computer games does a dot product. ChatGPT does a lot of dot products. Ultimately, it's matrix multiplication. Okay? And I'll tell you this. The AI revolution that happens in your lifetime could have happened in my lifetime because the mathematics was worked out in the 70s. Some of the math, not all, some of the mathematics was worked out in the 70s. The reason the AI object recognition, this, picture cats and dog only came out in your lifetime was because in order to do this kind of neuron mimicry, neural network on a massive scale, you need to be able to multiply a lot of matrix in a computer. And when I was your age, we couldn't do it. You know what's the final piece of the jigsaw? What happened is, and this is a story I make up, but it's approximately the truth. Some guy who's working with neural network, okay, has a son who plays a lot of computer games, and the computer games use what's called graphic card. Graphic card does nothing. It only multiplies matrix. Okay, so he borrowed that graphic card from his son. Now, I'm making this up. Maybe just play himself. He took the graphic cards and programmed it with artificial neuron. Again, the neuron does matrix multiplication. The graphics display does matrix multiplication. Logistic, binary classification, everything is matrix multiplication. Okay, plus something else. But the thing that you need a lot of is matrix multiplication. So you took the NVIDIA GPU and program it and made this groundbreaking AI. Okay, the math was worked out again in the 70s. I even met the guy who Professor Fukushima. It's easy to remember his name because it's the same name as the town where they had the nuclear incidents. Professor Fukushima actually came up with neocognitron, which is a model for doing the visual recognition. This thing that you say identify cats and dogs and whatnot. But there was no way he could do it in a massive scale and this quickly. It's only when the researcher, okay, used this GPU card from NVIDIA, which is like very primitive by today's standard, and ran this algorithm for like 5 hours. Okay, right now, all the AI that you hear, all the AI, GPT, whatnot, is based on some institution buying a lot of GPU cards, okay, and running this. Okay, now I'll give you how scary this is. In order to have a language model, say for Thai language, okay, Vistech, which is the research university in Rayong, where the first year just went to AI bootcamp. They actually bought, I don't know, 2 ล้าน baht worth of GPU card. But they didn't buy the same model as you did, obviously. Very expensive. And they ran this thing for 8 months to get the first language model. Okay, but at the end of the day, it comes down to matrix multiplication. Okay, long story short, when we go into the under the hood, how does your analytics work? If you don't understand matrix multiplication or matrix algebra, you have a hard life. So matrix, at least matrix multiplication, is very much in there. So that's story number 1. Okay. Story number 2. And I'm going to repeat this story with the Mathematica notebook when you have it. How do you train a machine to learn something? Okay. How do you train a machine to learn it? Well, you have to show it data. But not only show data, you have to have a way of saying that if I give you X and you give me Y, are you giving me the right correct answer or are giving me the wrong answer? Right? Okay. That is the basic of what's called supervised learning. Okay. Now, 10 or 20 years ago, when you were a baby, your mom did exactly the same thing with you. Pick up something, and if you say apple when it's a banana, your mom said no, right? But if you said apple when it's apple, banana when it's banana, your mom said, good boy, good girl. Correct? Correct? How do you learn apples from banana? From being shown a bunch of bananas and your mom saying that's a banana, being shown a bunch of apples and being told that's an apple. And more importantly, you try to call it first. And if you call wrongly, your mom says, no, 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 no. That's not apple. That's banana. Good, 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 good. That's banana and that's apple. Okay? This is called error function. Okay? This is called error function. Okay? How do you train a machine to learn apples from banana? You let the machine guess apples and bananas. And then you measure how much error it makes. And then you try to tell it to minimize the error. Okay? That's clear enough, right? That's clear enough, right? Yeah, you want to minimize error. Now imagine error is the height above sea level. When I say minimize error, what do I say? Go downhill. Go downhill. Right? Go downhill. So when I try to teach you, or your mom tried to teach you apple from banana, she's trying to tell you to minimize the error. When I teach a machine learning algorithm to minimize, the object recognition of this discrimination problem, I give it evaluation of an error function with the instruction to minimize. Yeah, minimize. How do I minimize? I imagine that the error is like a hill and I want to go down. I don't want to go up. Does that make sense? Does that make sense? So I'm going to call this hypothetical landscape error surface. I want to go downhill. Yeah, I want to go downhill. Now, here's what makes life difficult for you. If you are on a clear blue sky, see everything, you know where downhill is, right? Okay, now it's at night. Now it's at night. You can't see a single thing. You can't see a single thing. How would you go downhill? Well, you take one step around you and you see which one goes downhill, right? You try to find the slope. And you go down that direction. Okay? Long story short, how do you find the slope of a function? Calculus. Okay? So calculus allows you to evaluate the direction of downhill. That direction of downhill, if you keep going far enough, you go to the lowest possible amount of error. So calculus is what tells the computer to go downhill. The direction of going downhill is by adjusting the coefficient in the matrix. So now you understand why you can't do, machine learning or any kind of thing without linear algebra and calculus. Now, to be honest with you, integral calculus doesn't come in much here. Differential calculus comes in. And if you have a friend, you have differential equation, that also doesn't come much. Okay? But basically, yes, those are the two mathematical foundation that you need for any kind of machine learning. Most of it, most virtually all, not every. Okay, but modern day machine learning, you can't graduate from college saying you know things about machine learning and not understand how it links to algebra, linear algebra, and differential calculus. Okay, now, does that matter a lot? Well, there will be instances. Go ahead. Yeah, if you have to leave or something, just let me know beforehand and send me a signal. No problem, because some of you have project or whatever. Okay, but catch up. Dimutu is gonna put all this in a video. Hold on. If you go to YouTube and it won't be up tonight. Just put my name down. Oops. Okay. There should be some playlists in this and there somewhere. Playlist, sorry. So this is a YouTube playlist. I have a whole bunch of playlists. Now, these are data analytics from previous year. Again, you can use that, but like I mentioned, the field changes quite rapidly. Okay, so even the coverage is different. Yeah, so don't worry about class outline too much, but so there'll be one, I think, data analytics autumn 2023, and that will be your thing. Okay, and there's other. I wanted to show you earlier. Yeah, okay, this is the one. This is an example of, well, I was giving a talk at PyCon Thailand. PyCon Thailand is like Python conference. So in a second video, I would try to show how I work with Mathematica and then translate it to Python. So an example of how that work is like this one, I think. So even though it's a Python conference, the way I solve the problem is with Mathematica first. And so that's why it's Mathematica, then Python translation and so forth. Okay, so for applied digital intelligence, student, Python is going to be very critical because not everybody is going to have access to a closed system. Okay, so you work with and a lot of the basic functionalities you can translate one to one. Okay. Now, a lot of things in Mathematica you can't translate at all to Python, but a lot of things you can. Raise your hand if you are into bio tech area or genetic genomics or anything. You are? Okay. Now, for you in particular, Mathematica, Python is not enough. You have to pick up a third language called R. And this is because of a legacy. In other words, people who study genomics, they write a lot of software for doing genetics, engineering, solution finding, matching chromosome, all kind of stuff. All those libraries are written in R. Okay? So if you are focused on that, I would say that you can almost skip Python even. Just go immediately to R. Okay? Just for you. Just for you. So there are certain application dependent preference. Okay. Statistics used to prefer R a lot, but now Mathematica has more library in statistics, and so you can do that. Same with Python, but definitely genomics, genetics, research, you really can't survive without R. Okay, so just for you, pick up R. Okay, other people, Python, Mathematics. See, I can translate this. This is kind of like a fun thing where in the conference I would have English, Mathematics, Mathematica, Python, sort of like a translating. Okay, so this is Mathematics. You have to translate Mathematics into maybe Mathematica, and then Mathematica into Python, and this is all done. This is finance. It's got nothing to do with you, really. Yeah. Right. So back to our thing. This is the basis of all the AI's engine you're gonna have. Okay, except you can think of this as one unit of computation, right? And if you go to something like ChatGPT, you can ask something like, how many are there? parameter count for ChatGPT, and that's going to give you, 175 billion parameters. And I don't know how many neuron that is because each neuron has legs, right? And each leg is one parameter. So if one has 10 legs, you have to divide by 10. I don't know their inner architecture. But basically, they have millions of neurons. They have something like this. Now, might as well show you what it looks like. And I'll show you what it looks like. Again, I'll do a lot of this when you guys come back with a proper, this function, this neuron function. Okay, let's say my x, my x, oops, sorry. X is equal to, okay. Okay, let's say. Okay, try to keep your bathroom break during the break, okay? But other than that, no problem. It's called sigmoid function. Logistic sigmoid. Yeah. Now, this function, let's say I have all the A1, X1, A2, X2, A3, X3. I call it summation. I already sum it. Okay. So this logistic sigmoid is a function of summation. Yeah. Now, some input. Let's call some input. Okay. And I'm gonna plot it from, let's say, some input from -3 to 3 or something, because sometimes it can be negative. And let's plot it. Let's plot this guy. Oops. Logistic. Oh, input, not input. Okay. So that's that. Well, let's make it. Whatever. Okay. So let me make it a little bit more obvious. From -10 to +10, let's say. Okay. So you can see that this is a software. Why does it have to be a software? Why can't I just do this? Because it's chemical. In your brain, it's chemical. So it's not purely digital. Your brain is not a digital machine. Your brain is an analog machine. But this is sort of like analog to digital conversion. Basically, it turns a number into 0 and 1 with some fuzziness in between. Okay? So you can think of each neuron as, in a way, as a analog to digital conversion. And then you can think of a bunch of neuron as digital computer, right? Now, let me just play around with it. So how about manipulate the, I just want to show you, okay? Manipulate this, and from -A to A. Why can't I get, okay, A, okay? And A from, I don't know, 1 to 100, 1 to 200, yeah, whatever. Yeah, doesn't matter. I don't care. Okay. So now if I move this A, you can see that it's more sharper. Okay. So virtually it becomes a digital thing, right? Okay. So you can see that, you know, a chemistry engine in your brain can't do 0, 1, right? But based on this thing, there's a, you can sort of like, you can think of it as you look from a distance, it looks like, it's not, if you look really close, it's not quite, right? But if you look really far, it looks almost like a line, like a digital. And this is 1, and you have gazillion. Let's settle that. How many neurons do you have? Yeah, I get, it's approximately similar number. How many neurons in human brain? 86. Okay. 86 billion. Okay. It's yeah, okay. It's how many stars in a galaxy? That's sorry, how many galaxy in the universe? That's trillion. Okay. How many galaxy in observable? By the way, observable universe is not the whole universe. Yeah, 200 billion. I was giving you the wrong number. Okay, so remember that 200 billion galaxy in observable universe. Only 86 neuron in your skull. Okay, don't get the number confused. I got the number confused. Okay, good. So this is why nowadays this kind of when I was your age again, we started to do neural network research. Okay, and based on the computer I had at the time, maybe I could program 100 neurons. Okay, nowadays 100 neuron doesn't do anything. Okay, the language model, the one that you use in ChatGPT and all that, that's based on 1 million or 2 billion or something, 1 billion of neuron. Okay, and the number of parameters, that's if you count all the coefficient and all that. Okay, so we'll learn with that. You see how it works under the hood. Like I said, this is the idea. Okay, now good. We kind of like almost out of time, but before we go, I want to do a little bit of look ahead. Okay, so in this class, you're not going to be learning all about machine learning, right? You're not going to be learning just about how to program codes. You're not just going to be learning about how to clean data, but you're sort of like doing a mix of them. Now, I may not get the mix right. You know, sometimes I may place too much emphasis on this or that. And of course, over time, if you look back at, you know, my lecture 2-3 years ago, I would have focused on something else a lot more. For example, even last year, I absolutely excluded any kind of text or natural language processing. This year, I might have to. Now, my preference, okay? My preference is actually to reserve large language model like ChatGPT in a separate treatment under AI, because the bulk of AI has to do with natural language processing, okay? So I'll work on that. The technology is, you know, I have to wait on, you know, whether or not I have enough time to cover all the non-language or non-text data processing. Okay, if I have and there's time left, yeah. But right now, the way I design it, I would leave that for an AI course. Okay, again, AI is not just natural language processing, but a lot of AI that are currently viable or prolific is about text prompts. Okay, so what this means is that in this class, okay, in this class, because this is really your first, well, your main class about data analytics, what I'm going to do is focus on what you guys know what a Pareto law is. Well, it's like saying something like 90% of your profit comes from 10% of things you do or something like that. Okay, it's one of those things. Okay, 90% of the data analytics. If I say, okay, these are the data type. Okay, text, numerical data, graph, audio, video, chemical bond, genetic archetype, all kinds of. I list the 100 data type. Okay, I would say that 90% of your data analytics will be covered by 10% of the data type. Does that make sense? Does that make sense? Okay, so most of your job or most of the things that you're going to have to do won't be dealing with all kind of exotic data set. It will be dealing with just 1 or 2 data type. And that is most likely tabular and numerical. Okay, and that's going to pay off a lot. Okay, because just about, so if I were to say, this is my completely shoot from the hip, I would say something like 70% of life is tabular data, 20% of life is graph data, 10% of life is text data. Now, in the future, the text is going to be used as an interface for all this. So you can say that in the future, text is 100%. That's fine. But in terms of analytics itself, text-based is going to be still a minority. Okay? But then you would say, ask ChatGPT to build me a numerical model or something like that. Now, that's my guess. It may be wrong, okay? But that would be my preferred mix. So my responsibility is to make sure that at the end of this class, you have enough interactive visualization, statistical modeling, and machine learning tools in your tool bag to deal with tabular data and a little bit of graph data. Okay? A little bit of graph data. My research, I would almost say that last year I was commissioned by the Capital Market Development Fund to do a research. It was all graph data. Okay? So my life has become 90% graph data now. Okay, well, maybe not. Okay, but 80%, let's say. Okay, but for now, for you guys, maybe I'll give it 20% of the class coverage. Yeah, so hope that's fine. So you have, to an extent, you have to trust my judgment in terms of the mix a little bit. Okay, so, but I think I got the mix right. Come on. Okay, so yeah, that's it. There's no really homework per se. Okay, except make sure you've got all the yeah. I'm going to give you the DB2. Can you send you can have a line group, right? Have you signed up for the line group? Okay, I don't use Team. I think Line is enough. I mean, I don't want to use so many platforms. Final word is project. Again, I'm not trying to teach you how to do a project, but a project is a way of you framing what you need to learn. Okay. A good example would be I don't know if you saw from the graduating class, they were doing some project on, IoT measurement of the soil data or something. It turns out that to do that, they need to learn about something, maybe about soil mechanics. So they learn. So it's not about learning how to do a project. It's about using a project to organize your learning agenda, so to speak, right? Helps your menu. Now, we have a decent sized class. I really, don't want large class. This is about the right class. Ideally, I can pay you very, detailed attention, individual research project, but that's just probably not feasible. So for the class project, chances are we'll have to do groups. Now, groups, you're going to have to decide a little bit on. I don't want to really micromanage how you run your life, but a decent size would be about 4 or 5 person team, right? You should be able to, at the end of the project, I can ask you to evaluate your own contribution, your peer contribution, so that there's no free rider and nobody gets to do everything. But I think I'm not going to make it hard and fast rule, but I think 4 or 5 people person team is about right. More than that, then you start to lose focus. Okay, less than that, then it's not so much fun. Yeah, so I think about 4 or 5 sounds about right. So that makes it about what, about 4 or 5 teams. Yeah, 4 or 5 teams. You can start that conversation yourself in terms of, try not to just pick your buddies, okay? Just because chances are you have buddies, you have similar kind of skill and so forth, okay? So up to you. Do you want to pick the team yourself, or you want me to randomize or whatever? Okay, it's not a big deal. It's, adult education. You guys can manage your life, okay? But the concept of the project is to actually then, the difference between this kind of project and the project I do professionally is, the remit or the scope of my project to an extent is driven by the client, right? I'm getting paid lots of money to do their problem, not my problem. Whereas you are different. You choose your own problem. So you can choose your own problem based on your interest, but balance that with data, right? If you choose a very interesting problem and there really is no data and you're spending like half a semester contacting, organization, begging for data set or something, that's not going to be so much fun. Okay. Now, what I would suggest is you start playing around, go to, for example, Kaggle. Now, Mathematica has a lot of curated data inside. I don't want you to do that. That's too easy. We'll show you an example of that. Mathematica, like the data I show you, it's all curated. It has X and Y, and this, and there's no it's very well curated. Mathematica has a whole bunch of that. I would prefer you don't do that. I would prefer you to go to real source data. Like I did my problem with COVID. When COVID break out, I was hooking up with Owl in data and download their batch data by countries, by whatever. Okay, it's that kind of experience I would like you to play with. But Kaggle is kind of halfway in between. Kaggle is not an organization that has a certain set of data, but it's sort of like a platform for data scientists to play. So they have a lot of data. Same with GitHub. So these are the two things. But if you want to work with, say, weather forecast data, and you want to go to sub-Saharan humidity reading or something like that, that would be great. That would be great. I'd like you to go out there in the real world. Okay, so start having conversation among yourselves. Okay, and again, don't make it too easy. Okay, but don't make it impossible in terms of data access. Okay, so get something where it's data rich, and then you can do a lot. Okay, because I'm not going to have you come up with one data set and one regression equation. No. You're going to do a combination of unsupervised learning, supervised learning, visualization, all kind of stuff, right? So it's gonna be heavy duty stuff. Okay, so you guys know each other, right? So you're friends, so you know who's who. So you don't have to. Okay, so I'll see you. Oh, okay. Sorry. Am I early or am I late? Oh, I have an hour early, so I have plenty of time. Okay, I have plenty of time. So for some reason I wasn't. Yeah. Okay. So I don't know if you want to go through. Raise your hand again. Those of you who haven't got the Mathematica. Okay, that sounds good. That's okay. Okay. Well, maybe we can just leave early. Oh, I know. I can tell you a little bit about how I got here. That I'm supposed to give I keep forgetting this. It's self-introduction thing. You don't need to know very much about me. Okay? You don't need to know anything. You only need to know one thing, that I'm a product of something that we're trying to do with you guys. I'm a product of multidisciplinary education. Okay, that's all you need to know. When I was, my undergraduate years, I did my undergraduate in the US. Now, in the US system, it works slightly different. Okay, you don't belong to a department or faculty. Okay, you don't. You belong to the university, right? The only people who belong to department, like Department of Physics, Department of Economics, and so they are the faculties. They belong to the department. Graduate students also belong to the department, but undergraduates belong to the university. Okay, what it means is that if this were the case here, you wouldn't come to Basai, you come to Chulalongkorn University, and you would not belong to engineering or mathematics or psychology. No. You just belong to Chulalongkorn University. And then you would design your own major. Well, not design your own major. You sort of design your own path. And if your path concentrates a lot in political science, you'll be considered political science major. If your path involves a lot of physics, you'll be considered a physics major. Okay? So you can't learn just everything. You do have to concentrate, but you're not defined by the department. Okay? That's me. Okay? I'm from that tradition. So what I did was Well, long story short, I double major, one in physics and one in economics. Okay. Sounds a little bit silly, but one of the reasons that I study physics, not because when I was a young child, you always hear this thing about physicists. When I was very young, they didn't have a lot of political news. It was like physicists discovered this and that. So I thought that was pretty cool. And I spent my summer or after school with my aunt, who's a publication director, physics department. So I looked at some book, and it was like terribly dense. It's got all kind of symbol Greeks and stuff like that. So I just kind of thought to myself, this was apparently written for a human being. And I was a human being. I couldn't understand a word. Okay. So I thought, wait a minute, if it's written for a human being and I don't understand it, maybe I can understand it. So, it was my inspiration, I guess. And economics was just because I ran into a textbook from one of those old book sales. And the introduction chapter was written so well that, I thought economics was going to answer everything in the world. It did. But anyway, the idea is that at the undergraduate, you are not trained to be a technical person. Even when I majored in physics, I was not prepared to be a professional physicist. Okay? To do that, you need a master, you need a Ph.D. Same with economics. But with economics and physics, it gives me grounding in both the art and the social science. Okay? The concept here is that Chulalongkorn is still operating in a more, I guess, European as opposed to American way, which is students belong to department. So if you study physics, you belong to the physics department. If you study economics, you belong to economic department, and there's no such thing as a double major. Well, here it's integrated, right? Integrate art and science. Integrated here doesn't mean, and I don't mean to make fun of you guys, but some of the incoming students, they say, I like this thing, I like that thing, and my innovation is to put those things together in an app. That's not what integrated innovation means. Okay, integrated innovation means you integrate the knowledge, the technology from art, science, design, engineering, applied math, data analytics, all kind of stuff. That's you. Integration happens in your head. Then you produce the innovation. Okay, it's not that the innovation is one app that integrates three functionality that used to be in three apps. Okay, a lot of incoming students do that. There's an app for this, there's an app for that, there's an app for that. My idea is to have one app that does it all, and that's my integrated innovation. No, that's not it. That's not it. Integration happens here. Okay, so in this course, then, because it takes that kind of multidisciplinary integrated thing, you will learn not only say machine learning or data analytics or visualization, but as much as I can, I will give you perspective, even historical account of how various neural networks come to be. Okay, there's a reason why this algorithm that's in here called convolutional neural network is rooted in a 1958 study on cat's cortex. You know what a cortex is? Cerebral cortex. Sorry, it's a part of the brain that visualize. They study the cat's brain and focus on the way it processes light and so forth like that. There's shape detection and all kind of stuff. Eventually, that became neocognitron that I told you about in the 70s. You add neocognitron to the GPU. Eventually, you get to what's called convolutional neural network. And all the object recognition thing, whether it's in your ear or whatever, in everywhere, it's based on convolutional neural network. So you can say that convolutional neural network had its birth in 1958. Okay, so that kind of understanding is not just biology, it's not neuroscience, it's not just computing. So I would try to do that as much as I can, as will other faculty from this school. Okay, so that's it. That's all you need to know. That I'm a product of that system of education. My master was in operations research. I don't know if you know what that is, but that's also an integrated discipline. Brief history, and that's a fun thing. We might as well, since you can't play with computer today. You guys know, well, you know the World War II, right? Yeah. World War II was not the first war to be won by science and mathematics, but came very close. Anyway, you know what a battle of Britain is? Well, when Germany invaded Poland and France, and basically took over continental Europe. Next step was England, right? Great Britain, right? So the first thing you have to do is invade Britain. The first thing to invade Britain is to gain air superiority, take out the Air Force. Okay? Battle of Britain was won by Britain. Okay? Okay? And they won it because they have Spitfire that shoots down the, Focke-Wulf 109 or something. Okay? So Spitfire and Hurricanes, they fought brilliantly. But before they could fight the German airplane, they have to find it in time. Okay, they have to find it in time. So if they're not going to say, come meet me in high noon and let's go fight, and then doesn't happen that way. You have to detect. How do you detect an airplane? With radar. Now, radar was in the infancy during World War II, so they didn't have many of them. Nowadays, you can have a fishing boat about this big with a radar that's about this big, maybe cost $1,000 at most. Okay, and it would actually have the capability of World War II. Not quite. I'm just making. Okay, but back then they have huge antenna that does the radar detection of an airplane, and it's not mobile. It's huge. You have to build it. So they had to have a mathematical model of where to place it to maximize the coverage. That became a mathematical function. And that's sort of like the birth of operations research. It's research into military operations. Okay? Now, if you're not fighting war, do you don't need that anymore? No, everything is operations. Okay? I don't know if some of you came from family that runs a business that has to do with shipping, or at least require logistic shipping, right? That shipping, okay, it's an optimization problem. Okay, do you ship once a week with big trucks or 3 times a week with small trucks? That's a cost, that's a real cost saving thing, right? All this is done with mathematics. Okay, so my master, just a long story short, is that the only thing common in my study was it was applied math, but it was work everything, optimization, statistic, probability. How do you set up a queue? You go to McDonald's, right? Do you know why they have that many queues? Because it was solved mathematically that that's the fastest way. They can have 1 very fast queue. They can have 3 very slow queue, but maybe they have 2. Okay, now McDonald's may not do that, but I know my bank does. Because you have to do the optimization. Back then, this was for my bank. We have to study the queue of clients coming to the teller. Back then, it was sort of like beginning of mobile banking. So the mainstay of banking was teller. Okay, so we had to say, is it better to have highly proficient teller and everybody lines in 1 queue, or we have semi-skilled teller in 3 separate queue run in parallel, something like that. This was a mathematical problem. Okay, so my bank wasn't fighting a war, but the technique of this is operation research. Okay, so, and finally, my PhD is more like a neural network evolution. I'll talk about that later. But so my life story is not that interesting. What's interesting and what's pertinent to you is that because my life was based on multidiscipline education, okay, I could never be outdated. I can always reinvent myself. When I was in a bank, I did risk management, I did derivative pricing, all kind of stuff that wasn't in school. So the concept is not for you to learn a particular technique to use. The concept is for you to have multidisciplinary education so that when you graduate, you have certain skill you can use right away. But in 5 years' time, in 10 years' time, when some technological disruption happens, you can pick it up. Okay, that's all you need to know. Okay, that's all you need to know. I can't predict for you what's going to happen. Quantum computing, maybe. And we're thinking about actually a course in quantum computing. But I can't see the future. The point is that we can't predict the job market. We can only make you multidisciplinary enough so that whatever happens in the next 20 years, you can pick yourself up. Okay, that's the philosophy of this. Okay, that's what makes you better, because you're not going to be better coder than guys from computing. You're not going to be a better biotech, you know. So anyway, so that's that. I really, you know, just I'm killing time here, but we don't need to sit around that much further. But definitely next week, make sure you have all the things in front of you so we can start going through the code together. Okay, Kap? Okay, I'll see you on next Tuesday. Okay.